The energy transition, replacing fossil fuels with low-carbon energy sources, is a major societal challenge for the coming decades. For that reason, Infineon is active in various exciting applications such as solar, electrical vehicle or EV charging, and energy storage in order to participate in and drive this energy transition. Since e-mobility is a key pillar fueling the energy transition, EV charging stations are a key component to enable it. But how do they work? And what is the role of the gate drivers here? In this video, you will get a glimpse of EV charging stations and an introduction to gate drivers by exploring their functioning, utility, and key role in our future. Let's go then! An EV charging station converts green energy from the grid using alternating current power, also known as AC power, by converting it to direct current power, or DC power, which is then transferred to the electric car's battery. This EV charging station includes a number of system blocks, each enabled by Infineon components. The main two are AC to DC stage and DC to DC stage. Both of these stages convert AC power from the grid into DC power, which is then forwarded to the EV. In order to bring each of these main blocks to life, we need three key components: a microcontroller, gate drivers, and power switches. But why are they indispensable for operating an EV charging station? To further understand their role in EV charging stations, let's consider an analogy. Since the microcontroller runs a control algorithm that precisely defines how to steer the gate driver and the power switches, the microcontroller is the brain of this process. It holds the entire intelligence to the conversion of, let's say, 400 volts AC to an 800 volts EV's battery voltage. But for the microcontroller, or the brain, to communicate with the power switches, or the operators, a gate driver must be present to act as an interpreter, translating information from one to the other. This means that gate drivers receive logic-level signals, usually 3.3 volts or 5 volts, from the microcontroller and then amplify these signals, usually to 15 volts and beyond, to tailor them according to the power switcher's specifications. This is a crucial step since power switches present a significant input capacitance that microcontrollers would be unable to drive directly. Therefore, gate drivers provide the appropriate output stages to driver power switches of all kinds. After this communication, the power switches perform the actual conversion from AC to DC, thus being the operators of this conversion. But let's dive even deeper into the gate driver's functionality. The result of the microcontroller running through the control algorithm is a logic-level signal called a pulse width modulation, or PWM signal. This signal is usually 3.3 volts, and the currents are in the milliamp range, which is perfectly within the specification of typical microcontrollers. The gate driver represents a small input capacitance to the microcontroller, enabling microcontroller PWM signals to rise to high frequencies. On the output side, in order to make this PWM signal compatible with a wide range of power switches, the signal must be tailored, which means that it needs to be amplified. Usually, voltages needed to turn on power switches are in the range of 15 volts, but they can go all the way up to an output voltage range of 30 volts. The input capacitance of power switches is thus, by orders of magnitude, higher than the gate driver's capacitance. Therefore, directly driving a power switch without a gate driver is not feasible. Instead, gate drivers provide strong output stages to deliver high currents to drive power switches of all kinds, even at high frequencies. For this, gate drivers replicate the input PWM accurately within tight tolerances, while amplifying and tailoring the microcontroller signal to the power switches. But gate drivers have evolved over time, comprising additional functionalities beyond what has already been described. As protection features are an important add-on, advanced gate driver solutions already offer them as well. As an example, parasitic turn-on can become a challenge if a system operates at higher switching frequencies. This can lead to fatal system failures and must therefore be avoided. An active Miller clamp will solve the issue. Another example is short-circuit detection. If a short circuit is caused in a system, advanced gate drivers can detect them in a very short amount of time and can switch off the system safely. These protection features help customers minimize their efforts on a system level, since these are already fully integrated within the gate driver product. Still, sophisticated gate driver products go beyond even these protection abilities. Integrated monitoring features from gate drivers for, let's say, gate voltage or temperature monitoring are also available to aid the customer. These monitored parameters are provided to the microcontroller, which can use this information for intelligent system actions. In short, microcontrollers, gate drivers, and power switches are critical components to power applications, with gate drivers playing a key role in powering emerging technologies that will improve our future. You are now at the end of this video about the basics of gate drivers. If you need additional information, just take a look at our page at infineon.com/GD. Thank you for watching.